out. So that should be the first part of it, 19,932.2405, that's correct. And then we have Q was minus 600 times 14, 1.037 times 1.037 to the minus 13.
Oh, I did 14.
Well, because
you're using a different one. You're doing this one.
Yeah.
Okay, gotcha.
Which is going to give me 141. 1.037 raised to the minus 13 times 600 times 14 over 7. It's 141.
Yeah, I probably plugged in my calculator wrong.
Um,
I could probably just change this to 0.037 and then just change this to 13.
Yeah.
Do that.
And my guess is you may have done what I did.
Yeah.
When you're plugging it in, sometimes what the calculator will do is it will end up raising a whole bunch of stuff to the minus 13, and so you end up with a smaller number here.
Gotcha.
So I did that. I did this part first,
Okay.
and then multiplied by that.
Okay, yeah, I'll try that then. All right, cool. Try that. All right, thank you.
Yep.
We're actually logged in before.
Oh, a good 5 minutes ago this time.
We've got the wrong camera for Everett.
I think he changes it once he gets in there.
I'm not really there yet, but I can change it.
Right there.
Just sending you something?
No.
Okay.
Or did you just?
No.
Oh, okay. Well, I was like, oh, should I be mad at you?
Should I be mad at you? That sounds like a good idea.
Let me know. How you doing?
Great, Jade. How are you?
Are you okay?
I'm sober.
He's mad at you.
That's the problem.
Oh, you're doing good.
I had to go to office hours instead of Valhalla. That's how it's going, Jade.
All right.
Bah!
For what?
348.
Oh. Oh. Yes. I know. I heard that this semester is really bad. I took mine last semester and it's okay.
Our TA's like, yeah, I don't mind teaching guys stuff. This is like graduate level. You should be learning this instead.
Is that 348?
Yeah.
Yeah.
Immediate answer.
Is Valhalla like the name of some place in Pullman, or were you guys actually talking about you had to go to office hours instead of the afterlife of the Vikings?
Valhalla's a bar.
Okay. That was my second thought after the afterlife.
Just assume
I
it's
wouldn't have said bar.
the first,
Yeah.
the first option. We could just go to my actual.
Yeah.
Two birds, one stone, yeah. That was just sad because of 348 is making his life really hard.
Oh, yeah. I heard it's completely different.
That's exactly.
But didn't we took that last semester?
Yeah, we took it with,
The car guy.
he was cool, and then he had a cat.
I like it. Oh, yeah.
And he just like randomly like scream.
Oh, that's what that noise
That was
was?
his cat.
Oh, my. Okay.
This is what I,
They have lemons.
this is what I
What?
thought for.
They have lemons. Say K-Bay Obama. K-Bay Hablamos. I'm not Spanish, man.
Yeah. You pick 4 or 5
Je
minutes.
ne sais pas.
I'm taking my
Je
car.
suis
The mechanic doesn't know all the code.
Je parle français. Non hablo français.
You have to code for mechatronics.
Oui, je parle français.
What?
Un petit.
Yeah, j'habitais à Paris pour 13 mois.
Oh.
Dans 2012 et 2013.
C'est pas français. No entiendo. High school.
DC?
I just
I gotta
did what
go.
I knew.
I don't know what class this is. This is my class.
French 101.
I don't know about our installation.
I don't know.
one?
Is that, if you're taking electrical engineering, whatever that class is, actually, why don't we just move it over? Electrical engineering 432, looks like this is the homework.
Solutions.
Hey.
Also, does anyone know whose jacket this is?
No, I thought it was Noah's for the longest time.
For dinner.
No, yeah.
Wait a second.
Because I can really tell by the way he did it in class.
We want anyone to say.
Okay, so that's the nothing
We need,
number.
we need to be better.
Funny.
Okay. Like I'm looking at both of them, not just you.
Was this already here before?
Yeah, it was here when I came.
Cool. You're finally responding back.
So I just want to go.
Oh, it's already responding?
Well, not responding, just retaliating with another question.
He just, it's Ella's leg. So we get along.
Well, of course, we have classic.
So.
I feel like I have an answer to the question.
You can answer the first one?
Gonna get plastic.
Well, this is one of those things like, well, like red is a hot color, blue is kind of a cold color.
I would just describe.
Air, right?
What?
The air's on the outside.
Radiates electromagnetic energy, and us seeing people can actually detect what wavelengths are being reflected
Have you started the?
into our eye. We don't think of it as a wavelength, we see it as
It's worth it.
we see it as what we call color.
I can't start it until I finish. Okay, so.
Of course.
You
Do that. Frank made
I can have it in the room,
The controller always knows.
This is the classic that everybody, especially with.
How old is my son?
The watermelon ride also fire.
No, he didn't get into that phase until he was like 16.
Yeah.
He was only interested video games. He was only interested in video games. He was interested in Mario and Minecraft.
Oh, yo.
I've never seen that either.
Just the last video.
Right now, it's just Jason and Michelle in the front.
Right before, like, I have to do something really important. And then he's like, explain gravity to me, or explain why airplanes fly. I'm like, hold on,
I recognize that game. That was no, this one. This one. No, you do?
I don't really pay attention.
Okay, thanks.
I'm gonna go clean my room.
Yelling into
I
the
wish-
specific classic.
I wish I had.
Oh, yeah, no, that was.
Oh, it's 4:15, let's get started. Well, I'm assuming it's just the camera angle I'm looking at, and it's not an empty class of Pullman students, because I can hear you guys talking. So Pullman, can you guys see me all right? Are you seeing content?
Yeah.
Yep, it's good.
Okay, and Bremerton, can you hear me and are you seeing content?
Yes.
Okay, great. The content you should be seeing is, there were just a couple of other things I wanted to show you in QBlade. That the cameras got shut off, or at least from our end, it appeared the cameras got shut off. I want to just finish up a little bit of QBlade, and then we'll spend the rest of the time talking about vertical axis wind turbines today. One of the things I think we were on, there's this feature that you can do a finite element analysis inside QBlade. And I think I showed you guys that. And you can see that you have a nice, that you can enter in, forces at each element. And that you can see, based on the fact that when you can put in like the structural analysis of you can put in things like the Young's modulus, and you can mess around with the construction of the blade. Okay, there we go. So we can see the spur, and you can mess around with the thickness of the skin. So I showed you guys that, and I showed you the finite element method. What I didn't have time to show you is, after today, we're going to get into the static and dynamic analysis of the wind turbine. And one of the things we're going to be concerned with is that almost every part of your wind turbine is going to vibrate at various frequencies. And one of the things you can do inside QBlade is you can actually mess around a little bit with how your blades are going to, how they're going to oscillate. So there's this shape parameter that you can mess with. It might be easier if I show you the whole rotor. So I mentioned that when the wind is blowing against your rotor, this is going to cause your blades to bend backwards, what's called coning. And you can mess around with this, what's called this shape parameter, to see how they will bend back. And I mean, it's not quantitative, but it's just a kind of a qualitative sense of a fact that they bend back. The thing is, they're going to bend, but they're also going to oscillate. So they won't just bend back, they will oscillate around some average, and they'll oscillate back and forth. And when we're teaching students about vibrations, we usually start with assuming all the mass in whatever it is we're talking about, and when you guys take dynamics, is centered at a central point. We assume all the mass is at a point, and then we define a natural frequency for that point mass. But any object that actually has physical dimension is not going to have one natural frequency. You'll actually have multiple natural frequencies, actually an infinite number of multiple frequencies. But usually we're only interested in the first 3 or 4 natural frequencies, and those are called modes. So your blades are not just going to oscillate back and forth like this. There will be other modes of oscillation, where here the entire blade is oscillating, it's being back at one position and then forward at the same time, back at the same time, forward at the same time. You can look at the first 4 modes, and so actually when your blade will also be oscillating like this. And the third mode, there's going to be 3 waves. And the fourth mode, which we usually, I mean, in this class, we're really just going to focus on the first mode. Also, in this class, we're going to worry mostly about flapwise oscillation. But there's also edgewise oscillation, where the blade moves a little bit. where the blades oscillate forward and backwards within the plane of rotation. And there's also torsional. The blades will twist. Anyways, you can kind of play with this. It's kind of a nice visualization. I'm not really sure what the uses is besides visualizing some of these oscillations. The other thing you can do in QBlade, I didn't have time to show you, is you can do an actual simulation of how your turbine will behave in the real world. But to do that, you need a velocity field. So this tab, if you click on this tab, you can create a velocity field. Remember, your velocity isn't just a number, because your velocity is changing both in space and time. And so you can create, you can click new, you can come up with a wind field. This is going to be a wind field just for 60 seconds. And you select, okay, how big is your diameter? How tall is your hub? What is the median wind speed you want? And what is the turbulence intensity? And then I can hit create. What it's going to do is that the distance from this flat plane to this, what looks like a crumpled piece of paper, represents velocity. And so now you have a different velocity at each point within this velocity field. And this is only at a certain moment of time. So this should all center around the average wind speed that you set in that dialog box. And then you can actually, as you move through time, you'll see that your velocity at every single point changes in some realistic way based on the turbulence level intensity that you set. So if you set the turbulence intensity to 0, this curtain should look almost flat. And if you set the turbulence intensity really high, then I'd expect this to look more ruffled. Once you've done that, then you can actually create a simulation of your turbine. So I need to go here. I'm going to click new. And you can set a bunch of stuff in here. Again, you can set your hub height. For the sake of now, I'm just going to leave all this stuff as default. I'm going to use the wind field that I just created. And here I see a little model of my turbine. I can zoom in on it. And then I can run a simulation. And it's going to actually, so it is running this, I think it's just going to run for about 10 seconds of time. It tells me what the power being generated is at any given time. It tells me what the CP is at that moment in time. And in this case, it kind of generates an error because I created this rotor really quick just because I wanted to show this stuff off you. But you can see it is generating the vortices and the wake rotation behind the wind turbine. And for any moment in time, now that it's run the simulation, I can go back to any time step. Should be able to go back to any time step. And I can see oh, okay, so this particular design, I got a CP, I got a power coefficient of 36% in my numerical simulation. So those are some cool little added features of QBlade. And nothing I showed you today is something that you need for your project. It's just something I'm well, I should show you this stuff because it's kind of cool that QBlade can do this. I should say QBlade is very simplistic, right? The people who design wind turbines for a living, they probably have their own in-house software, like Vestas, GE, they probably have their own in-house software. They may very well start with QBlade. But certainly when they get into doing the finite element analysis, they use a more sophisticated finite element analysis software than QBlade. But the ability inside QBlade is a good start. Okay, so that's just some stuff from last week's lecture I wanted to finish up. I'm now, I'm now going to switch back to the document camera. All right, and we're gonna talk about vertical axis wind turbines today. And what I'm talking about today, this is kind of an indulgence to me to talk about vertical axis wind turbines because vertical axis wind turbines are what I've been spending a lot of time thinking about for the last couple of years. So vertical axis wind turbines, I've mentioned this before. It can be either lift driven or drag driven. And technically, the Savaronius wind turbine is this particular design of a wind turbine. And a Darius wind turbine is this particular design of a wind turbine, of a vertical axis wind turbine. A lot of people will call all drag driven vertical axis wind turbines Savaronius wind turbines. It's not technically correct. And the Darius, and some people will call, in fact, even this figure, which I got off the internet, refers to this as an H Darius rotor. This is not really an H Darius rotor. This is an H-type rotor. It is a vertical axis wind turbine. It is lift driven. It is not technically a Darius, but some people call all drag driven and then essentially call this all lift driven. Now, you might be wondering what's the deal with why this weird shape? The reason for this weird shape is not aerodynamic. It's not to become more efficient. The reason for this weird shape, which is called a troposkin shape, is this particular shape, this kind of egg beater shape. There are forces acting on these blades. So on this blade, this H shape, the blade's spinning. There are aerodynamic forces acting on the blade, and the force acting on this part of the blade does not match the force acting on this part of the blade. So this blade wants to tear itself apart. On the Darius rotor, the reason for this shape is this troposkin shape actually allows the forces acting on this part of the blade and this part of the blade and this part of the blade to be the same. So it's much easier to construct a thin, narrow blade of this shape that doesn't tear itself apart than it does for an H-type rotor. And incidentally, these are called H-type rotors because if you look at it on the side and you've got some bar holding it, it looks like an H. All right. Most of these, so as we've discussed previously, this design is going to have a very low, is going to be not very efficient. Because it's drag driven. And we've already discussed anything drag driven is going to have a low power coefficient. The reason that you sometimes see people promoting this style of wind turbine is because while it's less efficient, it also is fairly simple. So they can be constructed inexpensively. And they don't care what direction the wind's blowing from. So you don't need any type of yaw system. And if you're in an environment, like an urban environment, where the winds change direction rapidly and unpredictably, then this design can generate positive power under those conditions. Now, these types of wind turbines also don't care about the direction of the wind. They are more efficient. However, almost all of these are non-self-starting. And when I start talking about the aerodynamics, you'll understand why they're non-self-starting. What that means is on either this design or this design, if you build one of these systems, this will not start rotating on its own. You need to have some type of small motor to get it going. So you'll need to have a control system. You'll need to have a control system so that that will detect the wind speed. And when the wind speed gets high enough, a motor will kickstart the thing to spin. And then once the thing is spinning, the motor will shut off, the generator will turn on. Or you can have the generator also act as a motor if you're using a generator type that can easily also be, just the current can be changed direction and act as a motor. But it takes power to get them going. Okay. And the reason for this, explain the reason briefly. We'll get into some of the aerodynamics now. I have the wind. The wind is blowing in this direction. So I'm going to call this U infinity. And I'm going to look straight down on the wind turbine. So this is like a bird's eye view. I'm looking down. So I have a blade here. If this is a 3-blade, right. At this point, this blade with this wind speed, now at this point it's not moving, right? So there's no velocity because the blade doesn't have its own velocity. The only velocity, the relative wind speed is the wind speed from the wind. I don't have to worry about the motion of the blade. And this guy, I kind of exaggerated the drawing, but it's got an angle of attack kind of like this. And it's got some lift, and some component of that lift is in the motion, in the direction of this. So it's going to create some positive torque, and it's going to help this thing start to rotate. This guy, its chord line is like this, and its angle of attack is that. It's not doing anything. Well, actually, it might be doing a little. It's got some drag. Okay. This guy's not doing anything. If anything, and the amount of lift, it might actually be causing torque to go in this direction. It's really difficult to get these things started. Now, I'm going to talk about another type of vertical axis wind turbine called a variable pitch vertical axis wind turbine, which can be self-starting. And this fixed pitch vertical axis wind turbine I lost my train of thought. Okay, let's see. Fixed pitch, not self-starting. Right, its blade, this fixed pitch vertical axis wind turbine, its angle of attack, its pitch angle, which usually is 0. So its pitch angle is defined as the angle of the blade normal or tangent, normal to the radius or tangent to the circle of rotation. And this pitch is normally 0 and it's fixed. If the pitch here is the same here, is the same here, is the same here, is the same here, is the same here. A variable pitch vertical axis wind turbine, as the blade rotates around, the pitch can change. I've got some videos that'll make that a little bit more clear. So I'm going to go back to the PC. And start with this picture. So again, bird's eye view, and if this is rotating around, it's rotating in the opposite direction as the one that I just did. The blades are rotating around, and so like the idea is that the circle in the middle is the central axis. Okay, and this is a traditional fixed pitch. A cycloturbine, as the blades rotate around the central axis, they change their angle of pitch. Okay, and variable pitch vertical axis wind turbine is a mouthful. So cycloturbine is just short for vertical axis, variable pitch vertical axis wind turbine. And when you design cycloturbines, oh, by the way, gyro mill is another word that means the same thing. So when you design these things, it turns out that there's two really, what it turns out to be fairly complicated questions. One, how do you make the blades change their angle of attack or change their pitch as they rotate around? And also, what should the angle of attack be at each position? It turns out that that is a really difficult question to answer. And the best work on that was really just done like 4 years ago, and some papers that came out in 2017. One method you can get a cycloturbine to change its pitch is through this 4-link mechanism that this is a little animation I created in MATLAB to show this off. And this is a model that one of my students built of a small cycloturbine. So this is one method. The problem is that first off, the mathematics of how do you choose the length of each one of these links turns out to also be really complicated. And also, you're somewhat limited by what kind of pitching schemes, like what angles of attack or pitching can you have at each radial or azimuthal position around the circular path of each blade. So another method is having some type of cam. This is a little 3D model I made of maybe like a really simple cycloturbine, and I made it on a 3D printer at home. And so here you have each blade is connected to the central axis at one point by that's never changed, that the distance from the central axis never changes, and the back of the blade is connected to this cam, which is not quite circular. Now you have complete control over the pitching scheme. Although you can only set the pitching scheme to one particular scheme. And if it turns out that the one pitching scheme makes sense for one tip speed ratio and another scheme is better for a different tip speed ratio, you have no way to change it. So one of my students, I can't remember if this was last year or 2 years ago, came up with this idea of a 3D cam where the cam shape would change depending on the height. And so therefore you could change the pitching scheme by moving the height of these bearings in the cam. All right, okay, I think that's all I needed to show you on that presentation. All right, so another reason why vertical axis wind turbines are not as popular as horizontal axis wind turbines is, well, it seems like they're easier to build. It turns out that the aerodynamics, oh guys, do you guys remember how complicated the aerodynamics was for horizontal axis wind turbines? Because we've only spent like 4 or 5 weeks working on it. It's nothing compared to the complexity of figuring out the aerodynamics around these guys. So what I'm going to do is I'm going to show you people's first attempt to come up with an aerodynamic theory for our horizontal axis wind turbine, for our vertical axis wind turbine. And my goal here is just to show you what makes it complicated and I'm only showing you the most simple theory. All right, so there's been a lot of theories. What we're going to do is the most simple of the various versions. What we're going to study, and it's the only thing we're going to talk about, aerodynamic theory we're going to talk about in this class, is what is called single stream tube theory.
Yeah.
This was the first attempt to come up with an aerodynamic theory to predict the performance of a vertical axis wind turbine. Since this, there has been multiple stream tube theory. Since that came out, there was double multiple stream tube theory. And then there was an improvement on that, that was double multiple stream tube theory with expansion, with linear expansion. They don't know how to spell expansion. And then finally, really starting in 2007, there's flex line theory. Okay, but we're just going to focus on this today, and I'm going to show you one picture, maybe if I have time, of flex line theory. And if anyone wants to discuss flex line theory with me, they're welcome to do that in my office hours. Okay, and I can talk for quite a while about that. All right, so let me explain the situation. All right, I have, we're going to focus on an H-type horizontal axis vertical axis wind turbine. Rotating around like this. So I'm going to assume that it's straight bladed. And so, as I said, this is sometimes called an H-type. Now I'm going to look bird's eye view down on this thing. And I'm going to draw one blade for now. And I'm going to remind you that I should maybe back up a little bit. So this is called stream tube theory, single stream tube theory. The reason it's called single stream tube theory is, remember when we first started studying horizontal axis wind turbines, we started with momentum theory. Well, single stream tube theory is saying, okay, we're going to do the same thing we did for a horizontal axis wind turbine. We're going to assume that there's some velocity of the upstream, there's some velocity in the wake, and again, this is the simplest theory. What we're going to assume, we're just going to again assume that this clearly not one-dimensional bird's eye view of a vertical axis wind turbine. We're going to continue to think of an axial equator plane. And we're going to assume that there's some velocity here and some velocity here. And we're gonna continue to assume the same velocity. And I'm gonna call this velocity VR. So remember, and the reason it's called single stream tube theory is because from fluids, we think of a velocity of, if I track a particle of fluid here and watch its path, we just assume that this is one giant stream tube. And then you can kind of guess that multiple stream tube is like, okay, let's break this up into multiple smaller stream tubes. So remember that by the time the velocity of the wind gets to my wind turbine, it has slowed down. We're going to use the same notation as we did for a horizontal axis wind turbine. I'm going to say that the velocity here at my rotor, which is UR, and I'm going to say that UR is equal to U infinity times 1 minus A, my induction factor. That's exactly what we said for a horizontal axis wind turbine. And all of this based on single stream tube theory is an attempt to use horizontal axis wind turbine analysis for a vertical axis wind turbine. Now, so I'm going to use different colors. I'm going to have, when I get to this blade, I'm going to have a component of velocity that is coming from my wind velocity. The wind velocity at the blade is UR, which is going in this direction. But unlike before when I was talking about it not self-starting, this guy's rotating. This is purple for that. I'll use blue. This guy is rotating with some angular velocity, omega. And I'm going to give the radius of my wind turbine as capital R, which means that I also have a component of velocity, which is in this direction from the blade's point of view, and this is omega R. And also, what I really should do is I'm going to define the position of this blade relative to this. I'm going to call this phi. So phi is the azimuthal position of my blade. And so the relative wind velocity, the wind velocity that I want to know that is important aerodynamically in figuring out my angle of attack and anything else, is the vector sum of this velocity and this velocity. So this in red is my relative velocity, which is what the velocity I care about when I'm considering about the aerodynamics. Now, here's my model of our horizontal axis wind turbine. When I've got a blade here, and I figured out what is the relative wind velocity at this point on my blade. Yes, on a horizontal axis wind turbine, I need to figure out it's going to have a different relative velocity here, 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 and here. Right? We all agree, or hopefully everyone who's at least gotten started on the homework agrees that the relative velocity is different as I move along the blade. But once I figure out what that relative velocity is at this point, that relative velocity is the same whether the blade is here, 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 or here. The relative velocity does not depend on the position of the blade as the blade rotates around. Remember, the blade's rotating around pretty fast. Guess what's happening here? Now, this blade is at some point going to move. And when this blade is at this position, let's say this position, now my axial my velocity due to the wind, this is still the same, it's still going in this direction. But this component is now going like this. And so my relative velocity is now going this direction. Now, incidentally, this is my chord. So, and this is the relative velocity. So this angle here is my angle of attack. And this is my relative velocity. This is my chord. And so my angle of attack here, that's my angle of attack. Which means that this blade is not generating lift at this point. Okay? And so my angle of attack changes at each azimuthal position as my blade rotates around its central axis. And it's going to rotate around its central axis at relatively high speed, particularly if I've got a small wind turbine. So now you can begin to see why, hey, maybe being able to change the pitch of these blades is valuable. Because if I can change the pitch of the blades as it rotates around the central axis, I can attempt to have an optimal angle of attack to create positive torque at each angular position. You can also see why it starts to be incredibly difficult to calculate the performance or predict the performance of this type of airfoil, of a wind turbine, because my torque is no longer constant at each position. I have to actually calculate how much is each blade contributing to torque separately for each azimuth. And what I'll have to do is I'm going to have to calculate that torque and then integrate around 2 pi. Okay, so I'm going to relatively quickly go through a real quick analysis of this. So we can calculate, so now our relative velocity changes is now dependent on azimuthal position, where it wasn't before. But I can calculate my relative velocity, and this is going to be squared. And I'm just going to point out that this is as a function of theta, or phi, okay, which phi is my azimuthal position. And through a little bit of geometry and help with the Pythagorean theorem, I can show that this is equal to my angular velocity times r plus 1 minus a. I don't know what a is yet, but remember a is my induction factor. I need to find it. My velocity of my flow times sine of my azimuthal position squared plus 1 minus a. Remember that this expression here is my definition of my velocity, my wind velocity at my turbine. Cosine of phi squared. And so I can find my relative velocity. I can find my magnitude of my relative velocity as compared to the mean flow as equal to, and I'm remembering that lambda equals omega r over wind velocity. And the nice thing is now I only have one tip speed ratio. So that's nice, because my tip speed ratio is no longer really my tip speed ratio, it's now my entire blade speed ratio, because the entire blade has the same speed. So that's nice. So I can, using this definition, And putting a u infinity here, I can now define this term as lambda plus 1 minus a sine phi squared plus 1 minus a cosine phi squared. Through a little bit of trig, and I have a drawing here that explains it, but I'm just gonna write the equation down. I can also find my angle of attack as a function of my angle of attack, which again, my angle of attack is changing at each P position. And there's a little drawing you can do to get this, but my angle of attack becomes is the inverse tangent of 1 minus a u infinity cosine of phi over pi r, I'm sorry, phi angular rotation, so basically my velocity of the blade, plus 1 minus a u infinity times sine of phi. And if you look at this, this makes sense. It's these two terms, right? Where one of these terms is basically you're just doing a little trig, and this is one vector, and this is the other vector. And to find the inverse angle is basically, you can think of this as x and y on a right triangle. Okay. I can also write this alpha as tangent -1 of I can simplify this a little bit, and this is 1 minus a times cosine of phi over, this is using my definition of lambda plus tip speed ratio 1 minus a times sine of phi. I can go a little bit further. And I can, using my definition of tip speed ratio, I can say that this is roughly, I can simplify this roughly to lambda equals lambda plus 1 minus a sine phi, if lambda is large. All right. So now I've got this. I've got an expression. I can come up with what my angle of alpha is if I know my angle of attack. I can find my angle of attack if I know my azimuthal position around the turbine for a given tip speed ratio. Now I'm going to do something very similar to what we did with for a horizontal axis wind turbine. I'm going to apply momentum theory, and then I'm going to apply blade element theory, and I'm going to combine the two. So I'm going to start with momentum theory. We're going to remember that the velocity in the wake we had found to be equal to u infinity times 1 minus 2a. This is why a can't be greater than 1/2. Right? We found that several weeks ago. So my change in velocity from upstream to downstream. Is that a question?
In the book for alpha, it's the quantity of 1 minus a times cosine b over lambda. And for u rel over u, it's what you wrote on for alpha.
Oh, you're absolutely right. You're absolutely right. Yeah, all right. So that's what it says in my notes too. I'm racing because I know that we don't have that much time. this was lambda plus 1 minus a sine b, and alpha is approximately, using the small angle approximation, is 1 minus a cosine b over lambda. Okay, so what I want to do is I want to say like how much momentum is robbed from how much momentum is robbed from the fluid, from the air, which means if it's been removed from the air, that should be the momentum that's been added to my rotor. So to do that, I need to know the difference of velocity in the upstream and the downstream. So this change in velocity is equal to my u infinity minus my u wake. Now, well, this is u infinity is u infinity, and I just established that u wake is equal to u infinity times 1 minus 2a, which that means that my change in velocity is equal to 2a times u infinity. Right, so what I want is I want to find the force per unit height. The force per unit height of my blade, the force of unit height being imparted onto my blade, being imparted onto my rotor, is going to be the mass flow rate per unit height times my change in velocity. Well, I just found an expression for my change in velocity, and my mass flow rate per unit height is equal to rho a v, where b, or I guess this would be u. And with this u is the velocity, this would be the ur, this would be the velocity at my rotor. Okay, which I've already established that this is rho 2r, okay, it's the area, so it's going to be twice the radius because it's the diameter, times u infinity times 1 minus a. So I take this for my mass, and I take this, and I find that FD is equal to, this is going to work out, so I've got a 2 here, and I got a 2 here, so I got a 4r rho a times 1 minus a u infinity squared. And this is what I get from momentum theory. From blade element theory, or from analogy, let's say from blade element theory, I have that FD has to equal my number of blades divided by 2 pi, the integral from 0 to 2 pi of 1/2 rho my relative velocity squared times my chord of my blade times CL, my lift coefficient. But I remember my lift coefficient, I have to put that into the, I don't care about all of the lift, I only care about the lift that is tangent to the circle. Actually, probably be easier to say, that is normal to the radius of the blade to the central axis, which would be tangent to the circle, to the path of the blade is rotating around. So this ends up becoming cosine of alpha plus b, d phi, where again, so b is number of blades, and C is my chord length, and alpha, I'm sorry, and CL, which is a function of alpha, and alpha is a function of phi, is my lift coefficient. Okay, now I'm gonna take what I found in this formula with not the entire integral, I'm just gonna take it with this integrand. And I'm gonna equate this to the integrand of this. And what I'm gonna end up with is, which is exactly what we did in Blade in the horizontal axis switch rank. We came up with a formula for a force from momentum theory, and we came up with the force that the blades are generating due to blade theory, and then we set those two equations equal to each other. I'm gonna do the same thing here. What I'm gonna get is that A is 1 minus A, that's from this side. The rows cancel each other. After I integrate, this R cancels, I got a U in relative infinity here, these cancel. And what I'm gonna end up with is oh, I see that R gets brought down here. And I'm sorry, I said I wasn't doing the integration, but I am doing the integration. This equation is not an equation I can go any further with analytically. So this equation is going to need to be solved by iteration. Okay, so I'm going to have to make some guess. I'm going to make some guesses, and once I make some guess, I'll assign some other values, and then but you can't solve this analytically. So the trick the book suggests is we're going to define this new value y, and we're going to set y as equal to our tip speed ratio over 1 minus a. And now I can rewrite this equation as 1 over 1 minus a is equal to 1 plus 1 over 8 times bc over r times 1 over 2 pi, the integral from 0 to 2 pi of y plus sine of b squared plus cosine of b squared CL and this is times, I've run out of space here, times cosine of phi plus the inverse tangent of cosine of b divided by y plus sine of b, all of that, and all of that, dp. Whew. Now this will help us find a, and once we find a, we can find alpha. So the process is to assume a value for y. So here's your y. So 1, guess, I'll say guess. 2, using the definition for y, our lambda equals y times 1 minus a. 3, once I have this, I have an a, so I can calculate my right-hand side. And update a. That is 1 over 1 minus a, that's equal to my right-hand side. No, oh, I'm sorry. 1 minus a, this, I can calculate, this is my radius, I don't know my right from my left. Okay, and then after I've done that, now I can update y. And then repeat until a converges. And once a converges, then I can find out what my alpha is. Right? Now, when all that's said and done, I got more time than I thought I did. All right. Remember my power. Power P is equal to my rotational velocity times my torque. And my torque, I'm going to have to integrate from 0 to 2 pi of Q, where Q is my torque. dP, because I'm generating different torque at each angular position around the central axis. Remember, my torque is equal to my force of my thrust. This is the force, or the force tangent to the circle, the path of the blades, times the radius. And since I wrote this as total torque, and this is my force per unit height, this is my radius times my height of the vertical axis wind turbine. I should probably explain H. It's a little slow. My force per unit length tangent, using a very similar formula that we did in a horizontal axis wind turbine, is 1/2 rho u relative squared times, I'm only interested in the component of force that is tangent. And so I have to take the component of the lift force that is lift force that is tangent to the blades, and I have to think about the geometry and the drag force that is tangent to the blades, which is the drag force times cosine my angle of attack. And so, plugging this into this formula, I find that my power is the angular velocity of my rotor times the radius of my rotor times the height of my rotor. This was for a single blade, but there are V blades. I'm going to bring my chord length out to pi, and then I'm going to integrate from 0 to 2 pi of this expression, u relative squared times CL sine of alpha minus CD cosine of alpha dV. That gives me my power. Remember, I might be interested in my power coefficient. My power coefficient is my power divided by 1/2 rho. It's my area. My area is 2r, because that's my diameter, times the height, and then u infinity cubed. So, taking this expression and putting it in here, I can find that my CP is equal to lambda over 4 pi EC over r integral from 0 to 2 pi of u relative for u infinity squared CL sine alpha times 1 minus CD over CL tangent of alpha CP. Okay, and this can be solved numerically. And this is more or less the punchline. I want to emphasize okay, so to do this, you need to know alpha. right? You need to know alpha for each angular position. And the way you find alpha for each angular position is from the first set of equations that you have to solve iteratively. And also you need to find the angular induction factor, or you need to find the velocity induction factor. You need to find A. Okay, so you get that from the first set of equations, and then you can solve this. Very much like a horizontal axis wind turbine, you will find that A optimal is equal to 1/3, and you will find that our CP optimal, the highest we can get, is equal to 16/27, which is what we got for horizontal. So vertical axis wind turbines can be as efficient as a horizontal axis wind turbine in theory, but because they're not self-starting, and because you're not creating positive torque throughout the blade's rotation, they are not at fixed pitch. Vertical axis wind turbines are not as efficient as horizontal axis wind turbines. And however, a variable pitch can be as efficient. In fact, it can theoretically be more efficient slightly, but nobody's built one that's more efficient yet. I'd also like to point out this theory. I spent less than a class period walking you through this theory. I don't want you to.
Yeah.
You guys have a question?
Yes, sir. I think the power just 3 lines up, missing a 1/2 row.
CP?
This one?
Yep.
I do feel that there's a row missing.
2 pi times 2 row.
We gotta make sure we're talking about this equation.
Yes.
Yeah, I definitely feel that there should be at very least there should be a row in here. Give me a second. My point in walking you through this today was not to give you a, there's a one, oh wait, no, I'm sorry, that's the wrong spot. I'll put the row out here. There you go. I think that's right. All right. I want you to get a sense of like this is going to be done. This is for a single stream tube. This is the simplest theory that was available. And yes, I went through it in a day where it took me like 4 weeks to walk you through horizontal axis wind turbine theory. The only reason I'm able to do this in a day is because we spent 4 weeks doing horizontal axis wind turbine theory. This is much more complicated. It'd be much more complicated to program and to solve. And it's only the simplest theory. What we did with single stream tube theory is we said, here's my axis, my turbine, I'm looking straight down. I'm going to assume that my wind speed is the same everywhere. And I'm going to say there's one giant stream tube, and I'm saying this is my control volume. Yeah, it'll be easier if I just share with you this figure than it is. I was about to draw it, but the improvement over single stream tube theory is multiple stream tube theory. In multiple stream tube theory, we say, wait a minute, the blade is in a different position here than it is here. It's different here and here. So why are we assuming one axial, 1A? Why are we assuming the velocity slows down the same all across my radius? Why don't I say the velocity slows down at this point So A is different here than it is here, than it is here, than it is here, than it is here. Okay, and so this is multiple string tube theory. And then somebody said, well, wait a minute. The wind passes my blade here, that it's also going to pass a blade here. So I shouldn't think that there's one axial reduction factor. I should say that this is double multiple string tube theory, which says, let us figure out what is A here and what is A here, where I assume that the velocity gets slow. So this is U infinity. No, that's probably not that slow. So I have U infinity, and then my velocity here is U infinity 1 minus A, I'll call this A1, and that will also be my velocity here. But then when I get, or this becomes my new upstream velocity, so my velocity right at the blade will be this velocity times 1 minus some axial reduction factor here. So now I have multiple string tube theory. And then somebody said, well, wait a minute, this picture assumes that the wind is that, remember, the wind is slowing down. Well, if the wind's slowing down and it's incompressible, then it has to get wider. Right? When we did the horizontal axis turbine, we drew our control volume like this because we acknowledged that. So let us account for that by using double multiple string tube with linear expansion. And so this became and as you can imagine, the level of complication, we just assumed a single induction factor for the entire, that this is an order of magnitude more complicated. And that this is an order of 2 more complicated times 2. And that this is also more complicated. And then finally, let's take this. Well, first off, this assumes the wind is still going more or less in this direction, which it won't. The blade, if it's rotating around like this, is going to cause, if it's having angular momentum to cause it to rotate like this, the wing's going to want to go like that. And then also, why not, let's set an infinite number. Rather than find A here, A here, A here for a finite number of string tubes, let's look at an infinite number of string tubes. So the result, finally, as of 2017, look at this and I'm going to zoom in. This is flux line theory. I just said I was just going to talk about briefly. With flux line theory, you say that, so flux lines are lines that are perpendicular to your streamlines. Okay? So there is a flux line here. There is a flux line here. That's flux line number 2. So this is flux line number 1, flux line number 2. There's a third flux line here. And there's a flux line here. And what we do is we say there is a different value of A for each position along a flux line. So we come up with this parameter S, where S equals 0 here and S equals 1 here. And then we say that along this flux line, your A upstream is a function of S. And then along here, your A downstream is a function of S. And then we also come up with a shape parameter to control the fact that the path that each streamline, which is now infinitely thin, they're no longer stream tubes, they're streamlines, that your velocity takes a different path. So your velocity here might be different than the velocities here, as the wind speed medium. So this theory, again, came out in 2017. There were a couple of papers published on it, written by Zachary Adams, and I forget who his professor was. He got his PhD for writing this theory. And this is the state of the art for coming. And oh, the other thing is, the other theories, the single stream tube theory cannot be used for a variable pitch wind turbine because obviously A is going to change at each position because your pitch is changing at each position because you're optimizing it. And flux line theory can be used for variable pitch axis wind turbines, and it can also be used to help you optimize to find out what is the best pitching scheme. So now, for the first time, we have a fairly good theory that allows us to come up to derive what is the pitching scheme you want to get an efficient vertical axis variable pitch wind turbine. And that's really, that theory came out like 4 years ago. And that is all I have to say about vertical axis wind turbines today. And anyone wants to know more about flux line theory, send me an email. I can send you the papers written by Zach and his professor. And I also have copious notes that a former student of mine has made to try to explain it in more undergraduate terms. And I've made several notes on it. We've attempted to code it up. We successfully did part of the theory. We didn't do the second part of the theory. We're still working on it. All right, have a good day, guys. On Friday, we'll start talking about statics and dynamics and vibrations and a structural analysis.
Okay, yeah. .003. Remember I told you it's probably cheaper? We should just design an extension. Instead of carrying up
Pull this out of the back of the book. Pull that out of the back of the book.
Or getting it.
Probably.
Density.
Yeah, I didn't.
R123.
Yeah. Oh, I guess I didn't. I just started to take a look in the book.
Yeah, my other standby.
I'll take it.
That's what I did. Yeah, that's what.
So what'd you guys get?
And then, yeah, that's what we got.
You're
And
welcome.
then same math flow rate.
Steal this charger.
Yeah, that you even dropped the charger that I wanted to use. That's the
Yeah,
Oh, we just went straight to velocity.
sell it for good money.
Hey, goodbye.
Mass.
And then you have density.
Yeah, Jade, I'll try and finish it tonight.
Ooh, is it getting dark now?
It is.
I can finally use my light. These pants.
Did you send a friend request? Or just did you?
It's perfect.
Okay. Accept it.
Yeah, it's like, it's not really perfect, but they just extended this down to here. And then just left a hole. Oh, I want to do that, but I don't know how.
Buy some foam, or buy another helmet. Want to buy my helmet for me? It's too small for me.
And then I could
Chop
cannibalize.
part of it, glue it on in a good way.
Actually, I did just ask my dad to use his old motorcycle helmet that's a full face.
Yeah.
So he keeps saying that he wants to get rid of it. And I'm like, well,
You get the chance.
probably too old to be safe at 60 miles an hour, but it might do just fine at 30 miles an hour.
Thanks, we need more items for that.
Remember when I told you,
Hmm.
like every time I used to
They're
bring
gonna
this up, I
have
was
full
like,
name on the.
motorcycle helmet. That's what you want.
Well, yeah, but the main reason why I kept looking at my helmet is because I want something in the summer when I'm zipping around. Because I can tell you, even just motorcycling in a motorcycle helmet, you get really, really hot. Unless you're going literally 60 the whole time, which for a type of rain we do, that's few and far between.
That's true.
That's when you don't have to pedal.
What?
That's when you don't have to pedal. When you have to pedal.
60?
Well, on a motorcycle.
Why do you pedal on a motorcycle?
I'm saying, no, that's what I'm saying. You don't have to pedal on a motorcycle. For this bicycle, because I have to pedal.
I said you're going slower and you'll be hot.
Yeah, going slower, hotter. You just, this is my fall if I can get up when it's not raining. Yeah. Old motorcycle gloves though are definitely the way to go.
Yeah, I need to get some. When it comes to regular season, I'll probably need some regular gloves. Yeah. Oh, yeah.